Hello everybody. Let's talk about interaction of Carpathian mountain building with extension in Pannonian Basin, which is just behind Carpathian Wedge. We would like to define a predictive tool to help us with trap timing and other play concept elements. When we look at orogenic belts, we can group them into two different categories. One group is characterized by orogenic belts moving against mantle flow. Those orogenic belts would have a thrust belt, but no extensional region behind the thrust belt. In a contrary, the other group that would move in the same direction as mantle flow would have frontal thrust belt, but the region behind the creationary wedge would be affected by extension. Now imagine that when we look at theory about the displacement of a thrust wedge, the thrust wedge, before making new advance towards foreland, needs to build up. So this angle of the taper should eventually increase by internal building, and when energy is large enough, then the next migration event or advance event could take place. During that event, that angle goes down, gets reduced, and another cycle of mountain building would be needed. And we were wondering whether we can find any relationships between events here and events here. Our natural laboratory would be Carpathian creationary wedge here. We will be in Poland and Slovakia, not too far from Ukrainian border. Northernmost basin which we will use from Pannonian Basin system would be Eastern Slovakian Basin. It would sit right behind a creationary wedge. Starting in 90s, people published a lot on a relationship of extension in back arc position inside of these basins and contraction in the Carpathian wedge, but never made a step further. Always were happy with a decent correlation of entire time period of extension here with entire time period of contraction here. And I can mention names like Frank Horvath or Siert Kluding with different other names. We would like to make step further. We would like to see whether we can recognize individual cycles of mountain building and then advance towards the East European platform, and whether we can correlate those two cycles of events with anything specific going on in northernmost basin. We would use multiple methods. First method, we would go to field, measure shear fractures, calculate stresses, and based on their deformational record affecting different combinations of stratigraphies, we would separate paleostresses into certain sequence. Then we would sample along, we would do this for both basin and wedge. Then we would sample medium grain and coarser sandstones only inside of the accretionary wedge and try to use appetite fission track technique for indicating any episodes of exhumation, which we would interpret as indicating uplift of individual anticlines. It means mountain building going on. And then we would go to wells and do two types of analyses. One, for the accretionary wedge, we would like to look at penetrations of autochthonous neogene sediments underneath the accretionary wedge and see how far we can extend them underneath the wedge. Inside of the adjacent extensional basin, we would like to see whether we can recognize individual cycles of subsidence, tectonic quiescence, multiple ones. So let's start in a basin. So this is East Slovakian Basin. This is the boundary between accretionary wedge to the northeast and the basin. These are our outcrops. You can see that they are very close to the boundary because believe that the interaction between extension here and contraction here, if any, should be best indicated in the very north of the Pannonian Basin system. So we went to those outcrops, measured shear fractures and calculated paleostresses, separated them, and eventually I'm going to show you a set of maps starting with the early Miocene snapshot. Unfortunately, it's entire early Miocene time period. The problem was that it's a typical problem with extensional basins. All this fill is not usually very well represented on flanks in outcrops. So once in a while we would find something, bits and pieces. Most of the rocks would be either younger or most of them would be older. So the problem is that we couldn't see individual cycles of contraction of this direction northeast southwest, an extension of the same direction inside of such a long period of time. So we just saw that there was a stress regime controlling this part of the basin. It would be characterized by northeast southwest trending sigma 1, controlling mostly thrusting and strike slip faulting. With younger sediments we were luckier. We could recognize middle Bedenian switch to extension controlled by the same direction but this time extension. You would control normal faulting and strike slip faulting. And then there would be another switch back, slightly rotated maybe. Sigma 1 is still roughly northeast southwest, controlling strike slip faulting. And it took place during early middle Sarmathian. So we could look into northernmost portion of our extensional basin, right behind a Creationary wedge, and we can see it underwent switches between extension and contraction along the same trajectory. So cycles of contractional stresses, sigma 1 would be similar orientation to sigma 3 of extensional cycles. So we could see some switches back and forth. Now we could look into wells themselves for the entire basin, group them into 4 groups depending on region of the basin, and suddenly we can recognize that there was quiescence prior to Carpathian, then Carpathian subsidence, then either quiescence or even uplift, then another subsidence, middle Bedenian one, then quiescence, and then we kind of lost a recognition of quiescences and subsidences becoming much more pale in comparison with the main ones, because the system became dominated by thermally controlled subsidence. Nevertheless, we could recognize 3 periods of quiescence and 2 periods of subsidence. Now we can move on to a Creationary wedge. Over here you are looking at a large region from roughly Krakow level all the way to Ukrainian border, where we constructed 5 Trans-Carpathian balance cross sections. Before doing that, we were in a field from March till November. That was the longest field trip of my life. We were taking 3-week shifts, then a few periods at home and then back. We mapped zone roughly 10 kilometers plus minus around each transect to verify that the maps we were given were right. They were actually fairly good maps. The same applies to stratigraphies they recognize, because we've done our own biostratigraphic verification of stratigraphies at all of these outcrops, and we couldn't find dramatic mistakes. Here we measured shear fractures, calculated paleostresses, and regime was with sigma 1 northeast southwest oriented, relatively monotonous system during the entire time of its development. But appetite fission tracks could help us with individual details. because they would indicate mountain building periods for us. So we went to those outcrops and sampled. Not all of them would have medium grain sandstones or coarser sandstones that would allow us to sample and separate apatite grains. Then not all medium to coarser sandstones would give us 20 or more apatite grains. So here we are looking at subset after those two separation events. And eventually some of the apatites in yellow outcrops weren't buried deeply enough to get thermally reset. So they couldn't really help us with indicating anything about mountain building events. They could just help us with fingerprinting their provenance. So the only helpful subset is the subset with numbers, which represent apatite fission track numbers. We can actually color code those numbers, making them blue or purple if they are oldest, making them yellow if they are youngest, and anything in between. That eventually could help us even if we know geometry of individual thrust sheets or groups of thrust sheets to contour, and we would have rough indication of what we should expect from mountain building. The youngest one really capturing only this portion of thrust belt, mostly older episodes here, individual main structures undergoing and helping with mountain building. Apatite fission tracks could help, but it's relatively one of the coarser data sets. Eventually with the balancing, I'm going to show you only central transect in its deformed state and restored state. We can move towards the east, its neighbor, deformed state and restored state, and eventually we see the easternmost one very close to Ukrainian border, deformed and restored. Each of those transects, but also regions among the transects, would have quite a lot of deep structural wells drilled by Polish Geological Survey, and they would allow us to see what's the age of autochthonous neogene sediments underneath the wedge. And that would be the data set that would allow us to construct locations of front of Carpathians for certain periods of time: Sarmatian, late Badenian, middle Badenian, early Badenian, Carpathian. And we should really drop this part because there's enough wells really to help us. So we would be really looking at Carpathian and younger ones. And this is what we've learned. We could recalculate that for a particular period of time. We could really reliably understand Carpathian to early Sarmatian what was the advance of frontal thrust in kilometers per 1 million years. And we could suddenly recognize advance period during Carpathians, slow down indicating mountain building, then subsequent advance towards northeast during middle Badenian, then slow down indicating uplift, mountain building, and perhaps another advance indicated, although most of the transects further west, apart from easternmost ones, already indicated that Carpathians were done with their docking against a platform. So I don't know how reliable is this advance here. And now we can start comparing individual data. We can start with the best ones. Advance versus mountain building periods indicating by behavior of frontal thrust. We can compare it to subsidence curves, and suddenly we realize that each time when we have advance, there will be prominent subsidence. From seismics we would know that it's tectonically controlled, extension not calculated by roughly implied would be north, east, south, west. And then each mountain building would be associated with a quiescence. Now we can compare all four data sets. So we can see contraction, extension, contraction in the northernmost portion of East Slovakian Basin, entire early Miocene, middle Badenian, early Sarmatian. and we can see how it fits to what we can learn from other data sets. Appetite fishing track data, the more numbers we had for a particular period of time, more hits we had, indicating that that was the time when active exhumation was going on, which we interpreted as uplift. It means mountain building. So contraction, prominent mountain building, but just like with contraction, appetite fishing tracks couldn't really help us with the definition of more detailed switches back and forth. So as a result, we can see advance of frontal thrust, and we see slowdown in exhumation activity, if we can even say that. But definitely we see advance and prominent subsidence behind in extensional basin. Slow down mountain building, we can see some mountain building in appetite data, and we can see also quiescence in extensional basin. We can see very prominent advance of the frontal thrust. We have no appetite data indicating any exhumation mountain building, but we do see in extensional basin that was really undergoing some prominent extension and subsidence. Slow down mountain building, we see it indicated by appetite fishing tracks, again kind of a picking up. Quiescence in extensional basin, and then the rest is kind of a difficult to see. Maybe some advance, maybe a little bit of subsidence. I don't know. So imagine looking at this seemingly academic tool and now turning it into predictive tool for exploration. Imagine that we are an oil company and we have a blocking thrust belt. No data on back arc basin behind it. We can work out our trap timing, but it will tell us exactly where we should expect quiescence periods of time in back arc basin. If we work out advanced periods of our thrust belt, we would know exactly when to expect potential reactivation of back arc traps or formation of new ones. Now imagine that we are an oil company with block in back arc basin and no access to any data in adjacent thrust belt. If we work out back arc basin trap timing, it would be coeval with the episodes of thrust belt advance. If we understand timing of cycles of quiescence in our back arc basin, that would be the timing of out of sequence thrust belt trap reactivation in most of the creationary wedge. So risk of breaching of already pooled hydrocarbons, if we can prove that they were there, and formation of new traps in the front. But it's not all about just trap timing. We can learn a lot about other play concept elements. We can look at back arc extension and understand that that would be the time when thrust belt increases that would be the time when thrust belt moves towards the foreland, in downflexes the foreland plate, and there would be a surge of basinal conditions in foreland basin towards the thrust belt. So back arc extension would indicate good periods of time of potential source rock deposition for us in the foreland basin in front of thrust belt. Or understanding back arc quiescence periods, that would be the timing of important shed of siliciclastic sediments from our thrust belt into adjacent foreland basin. So quiescent periods of time, we should see deposition periods of reservoir prone rocks. If we understand back arc extension pulses, these would be the pulses when a foreland would downflex against advancing thrust belt, and its forebulge would migrate landwards. That would translate into migration focus moving landwards. So imagine the possibilities. They would be basically endless. Thank you very much for your attention.